Well, why should we call this planet Earth when it is ocean? We could also say, why should we be concerned with the Atlantic meridional overturning circulation when it is Pacific? But anyway, probably don't need to motivate you to be interested in the ocean as you're all here, but I just want to recall that the ocean provides important services to us, including food, but also in terms of taking up carbon to mitigate global warming and taking up heat to slow global warming somewhat, but this comes also at risks, and the risks are known as extreme event, so ocean heat waves, which bleach the corals, and linked to ocean uptake, it's ocean acidification. Then we have also changes in the circulation, which lead to ocean deoxygenation. So there are many topics that could be tackled in these 40-minute lectures, linking the carbon cycle and deep ocean circulation, and I didn't know actually what to talk about, so then my excuse was I selected just 4 topics and provide some insight into the linkages between carbon cycle and biogeochemical cycles and the circulation. The first example is the long time scale of anthropogenic CO2 uptake governed by the slow deep overturning circulation. Then looking at deoxygenation in temperature stabilization scenarios over the next few millennia, and then switching the timescale, going to the past and looking at the reconstruction of past Atlantic meridional overturning circulation from multi-proxy data that Edouard already introduced, and then some final thoughts on the glacial CO2 increase. Anthropogenic carbon uptake, as you all know, by burning coal, oil and gas, we pollute our atmosphere, and this leads to global warming. And part of this carbon that is emitted into the atmosphere is taken up by the ocean, and this is pretty much a top-down process in the sense that the CO2 emissions are added to the atmosphere. This raises the atmospheric partial pressure of CO2. It gets then higher than the average ocean partial pressure, and so CO2 is invading the ocean by air-sea exchange, and the rate-limiting step of the uptake is actually the mixing of the excess or anthropogenic carbon from the surface layer to the deep, and this is of course mediated by the circulation. In addition, we have some climate feedbacks, so these are sort of climate-driven changes in the solubility. If it's warmer, a gas is less soluble. That applies for carbon as well. Then we have reduction in sea ice, changes in circulation due to changes in wind stress or freshwater input, etc., and also some changes in the biology. So what drives this top-down process on the longer time scale is sort of the slow deep ocean mixing or overturning. And what you see here is a plot showing the radiocarbon ventilation age for waters below 1500 meters. So you have an age scale that goes here from bluish, so that means decadal to century age, up to red colors, which mean an age of 1200 years. And this is sort of an indicator how long it takes for the water from the surface to reach a certain place in the deep ocean. So you can see that the deep Atlantic is sort of ventilated on decadal to century time scale, whereas the deep Pacific and also the deep Northern Indian, it takes quite a long time, many centuries, up to a millennia, to actually bring the water from the Southern Ocean surface into the deep Pacific. And this has consequences. And the consequences is that there is a lot of inertia in the system as soon as the ocean is evolved, being for carbon uptake, be it for heat uptake. So in the case for carbon uptake, it takes many centuries to actually tap into the full potential of the ocean to absorb CO2 from the atmosphere. And this is illustrated by these sections here. You have here a depth scale from the surface to the ocean bottom, and from then a latitude from south to north, so it's a section through the Pacific, and it's showing the excess or anthropogenic carbon, so the change in carbon in a scenario simulations versus one of a control run. And you see by year 2100, the excess carbon has penetrated in the upper ocean, in the upper 1,000 meters, whereas the deep ocean is still void of excess carbon, of this anthropogenic perturbation. 400 years later, this particular model, it's one of the NCAR model, Earth system models, shows that the carbon has been mixed in the Southern Ocean and also traveled to some extent towards the North Deep Pacific, but there are still areas that are free of anthropogenic carbon. So the take-home message here is basically it takes centuries to mix the carbon from the surface to the deep ocean. And the consequences of this is that atmospheric CO2 and also surface warming will stay elevated also for centuries and millennia, even after stopping emissions, as done in this scenario. So you see here a time scale from 1850 to year 2500, and on the y-axis the atmospheric CO2 concentrations. So CO2 emissions led to an increase of CO2 in these high scenarios to about tripling the CO2 concentration, and after stoppage of emissions, the CO2 decline is fairly slow and the CO2 remains elevated for a long time as this uptake process by the ocean is so slow. I mentioned that there are feedbacks in the system, so we get with elevated CO2 surface warming, we get changes in wind, in freshwater fluxes, and you name it. But those feedback play, at least in the current class of models, a relatively small role, as in the model I show you, but also in other models. So basically we can disentangle that by factorial simulations, so running the model without seeing the climate change, and then it simulates a certain uptake. What you see now is a section through the Atlantic. So you see here the penetration by the AMOC, the Atlantic Meridional Overturning Circulation, bringing excess carbon into the deep, and ventilation pathway from the south through Antarctic bottom water. The point is here, when we now allow also climate to play out, and by difference we can estimate how much this contribution is of these climate feedbacks to the changes in dissolved inorganic carbon in the ocean. And then you see here first on the right-hand side how much the carbon is different when climate is allowed to vary in the model. And you see then here in bluish color a reduced uptake due to a slowed circulation and due to slowed solubility in the deep Atlantic, and more uptake in the Arctic as the sea ice is gone away, and so sea ice is impeding the air-sea gas exchange and hindering the uptake of excess CO2, so there is more uptake when the climate feedback is allowed. In addition to this air-sea flux feedback, in quotes, which sort of alters truly the carbon inventory in the entire ocean, there is also a reorganization of the tracer distribution taking place within the ocean as a consequence of changes in ocean circulation changes, and these are quite noticeable. As you can see here, these tracer reorganizations due to a weaker and shallower AMOC in this simulation leads then to less carbon in the upper Atlantic and more carbon in the deep Atlantic. So this circulation sort of plays out to also alter the distribution of carbon within the ocean without actually changing much the global carbon inventory. You can see the numbers here are quite small in comparison to the overall uptake for this particular simulations, a few percent. So with this, it's perhaps time to say a few words about the interplay between circulation and marine biological cycles. So as you know, there are organisms in the surface ocean which do photosynthesis, which assimilate carbon and take up nutrients, and then they get eaten, and there are organisms that produce these nice shells made out of opal or made out of calcite, and at some point the organisms die or they exudate materials, particles are formed, and these particles are settling under the forces of gravity. And we can take a 1D view of this interplay. The role of the circulation is basically bringing nutrient up to the surface, because on average the surface ocean is depleted in nutrients, in phosphate, in nitrate, in silica, in carbon, because the organism take up these nutrients. So a part of the nutrients is transferred from the inorganic form to the organic form. And at some point, as I said, this leads then to particle production, which settle to the deep ocean. And what happens then in the deep ocean is that this organic matter, the shells of opal, shells of calcium carbonate, they either dissolve or remineralize, and this leads to a release of the nutrients of phosphate, silicate, and carbon, and at the same time, it also leads to a consumption of oxygen, so that we have high nutrients and low oxygen concentrations in the deep ocean. And a similar cycle applies for the carbon isotopes, here given in delta C13. Edouard has also mentioned this this morning. There is a fractionation going on during photosynthesis, and so this plays out that delta C13 is high in the surface ocean and low in the deep ocean. Of course, it's not so simple as the 1D view, but anyway, the 1D view can explain some observations. For example, you see here a profile, typical nutrient profile in the ocean with depth, and so at the surface, the nutrient concentrations are low. At the intermediate depth, where most of the organic material is remineralized, there is a maximum, and then nutrient concentrations are also low, high in the deep ocean. In addition, there is sedimentation going on of these particles and ocean sediment interaction, which are quite important for long time scales, but I will not talk today about this. But we shouldn't forget about this sediment reservoir. Anyway, there was a lot of debate already about the conveyor belt, and my pick on the conveyor belt is coming in the next slides. Basically, it's a 2D view of this marine biological cycle, and you have sort of, we agreed on maybe that in the surface ocean we have low concentration of nutrients. If there is now sinking of water, like in the North Atlantic, then young, so water that was in recent contact with the atmosphere and which is nutrient and carbon poor is entering the ocean. It doesn't stay in the North Atlantic, as we have learned this morning, but it is transported southwards, it is mixed in the Southern Ocean, and it's eventually going into the North Pacific. And during this travel, which I think Wally Breaker had in mind when he talked about the conveyor belt, these water masses are picking up nutrients, like suitcases that you throw on a conveyor belt. Here, these water masses pick up the nutrients that are released due to the remineralization or dissolution of the particles. And so, the older the water gets, the more nutrient-rich they get along the flow path. So, on the end, you have old, nutrient and carbon-rich, and oxygen-poor, and delta C13 poor waters in the part where the oldest parts of the ocean or oldest waters are found. And this is shown here. So that's sort of a other way of presenting the sketch of a conveyor belt. You have here now a section through the Atlantic, okay, I should show it here, through the Atlantic, around Antarctica, and back into the Pacific. I will use this sort of slides or display quite a few times. So a section displaying both the Atlantic, the Southern Ocean, and then the Pacific. And I have a color scale, low carbon, white, high carbon, bluish color, and you see here the AMOC, the circulation brings young carbon-poor water into the deep Atlantic, which is mixed in the Southern Ocean. Part of it is flowing northward again as Antarctic intermediate and mode water, and part is flowing northward as Antarctic bottom water. The other part is flowing into the deep Pacific and return then back to the Southern Ocean. And you see the oldest and most carbon-rich waters are found here in the North Atlantic. Perhaps you remember the slides that I showed before. The deep North Pacific had radiocarbon ages of about 1,200 years, whereas here in the deep Atlantic, the radiocarbon ages were much younger. And so this goes together. So in this way, the sketch of Wally Bröcker, I think, is correct, but it shouldn't be, of course, overinterpreted. It's just a cartoon that depicts this pickup of carbon when the water is aging in the deep ocean. The same applies for oxygen. Now the color scale is a lot of oxygen is white color and no oxygen is brownish color, and you see young oxygen-rich water in the deep North Atlantic and old oxygen-poor waters in the North Pacific. The two tracers don't completely match one-to-one. There's, of course, also additional complexity, but basically the principle of the conveyor belt applies here in this sense. This brings me to my second example, and that is ocean deoxygenation, projected in multimillennial global warming simulations. And I thought this would be sort of a nice, well, I'm not sure it's a nice example, but an illustrative example, as ocean deoxygenation can, of course, have severe consequences for aerobic organisms such as fish. So what did we do here? We use a class of model which is very, very much at the other end of the one that was presented before the lunch by Anne-Marie. We use a coarse resolution Earth system model of intermediate complexity where a geostrophic frictional balance equation is solved, but the ocean is represented in 3 dimensions. The model runs very fast. So we can do ensemble simulations, and we can even run the model out for 10,000 years or 100,000 years. So we did here 4 scenarios, and in these different scenarios, temperature stabilized by 2300 AD at different levels, and for each of the scenario, we ran an ensemble with 100 members, where we varied the remineralization rate and diffusivity or circulation within the model, and picked then those runs that best or that has show good agreement with observed oxygen and radiocarbon distributions. So this is the results here for temperature. So you see here, start at 1800 or so, go to 2100, then we have a split in the axis, and then we let the model run for another 8,000 year to year 10,000 AD. So it's really quite a long simulation. You see that temperature is stabilizing at around year 2300 here in this high scenario at around 9 degrees Celsius, in these intermediate scenarios at around 3 degrees Celsius, and these bluish scenarios, they meet sort of the temperature goal of the Paris Agreement from 2015. So what are the consequences of such scenarios for the circulation? You see here now sections through the Atlantic from south to north and from surface to the deep, and you see the stream function that Juliette explained to us this morning. So basically we see here the overturning circulation going this way in the upper Atlantic. It has a strength in this model of about 17 Sverdrup, pretty much in agreement with the observation. And then at the year 2050, when global warming has taken place, the overturning function has weakened, so there's a less vigorous ventilation here. It has also become shallower. And at the new steady state, at year 10,000, the overturning circulation has even become stronger. So there is an evolution from pre-industrial to a weakening to a stronger circulation. And similar for the deep Pacific. You see here the numbers, right? We have this overturning flow, deep Pacific water flowing northwards and then returning and flowing southwards again. We have here the pre-industrial value, a weakening, and a stronger circulation at the end. And that's even the case for a climate change of 1.5 degrees Celsius, which is probably quite unrealistically that we manage to keep climate below this limit. So, what are the consequences then for the oxygen inventory of these circulation changes? Of course, if the circulation is getting slower, that means the age of the water is getting older, so we expect more oxygen consumption. And that's exactly what is happening in the model. You see here a change in oxygen. In the high emission scenario, you see a decrease of about 40%. That's the global mean oxygen inventory that is decreasing by this large amount in this particular model and scenario. So it's a huge change. We don't need to worry about oxygen ourselves in the because the atmosphere is a huge reservoir of oxygen. The ocean only stores about 0.5% of the oxygen in the combined atmosphere-ocean system, so we don't need to worry about this. But for marine organisms, this could be quite a problem. We have also declines in the other scenarios, and towards the end, in the high emission scenarios, we have lower oxygen values than at the beginning, whereas in the other twos, we have other freeze scenarios, we have higher oxygen inventories. There are opposing effects. One is with water age, and the other one is with solubility. So in a warmer world, oxygen is less soluble, which tends to reduce the oxygen. What I would highlight or would like to note you on this slide is actually the long time scales involved. So we get the oxygen minimum here many years after forcing has been stabilized or temperature has been stabilized. So there's a huge lag and inertia. So even if we manage to stabilize the climate system, there are still some impacts that will continue to aggravate for centuries. And it also takes a long time to recover then to some more favorable state for aerobic life. Turning a bit to the mechanisms, now coming perhaps a bit more complex and more for the specialist, you could say that these peak changes are driven by changes in the marine biological cycle that I explained to you somewhat before, and by warming. So you see the whole ocean is warming, which reduces the solubility of oxygen. So throughout the ocean, in the Atlantic, in the Southern Ocean, in the Pacific, we have less oxygen. The rearrangement or the slowing of the circulation leads to changes in the oxygen consumption within the ocean, which leads to a decrease in oxygen very much in the deep ocean, and in this particular model somewhat to an increase on average in the thermocline or in the upper ocean. And we can look at this a bit in more detail, in that we have again the same panel here showing the oxygen change due to this biology circulation link, and we can compare that with the age of the water. So in this model, we have a tracer added to the model, which ages when it is transported below the surface each year by 1 year. And so you get the age of the water within the model, and you see that the deep Atlantic and deep Pacific have aged by up to 200 years. And consequently, there was more time for oxygen to be consumed, as these water masses stayed a long time away from the surface before they get replenished again by exchange with the atmosphere. Whereas in the upper ocean, the ventilation age at peak, it's a transient thing, increased somewhat, and so this explains why we have here a bit higher oxygen concentration. And in addition, the export of particles decreased in the Atlantic and in the Pacific, which also tends to favor a bit a positive trend in oxygen. So the message is sort of okay, long time scales and also opposing processes, solubility, circulation, which may play out regionally quite different. And another consequence of decreasing oxygen in the ocean, it has an impact on the emission of another greenhouse gas, that is nitrous N2O. It's also quite a powerful greenhouse gas, and due to a decrease in oxygen, we also get a decrease, or due to these changes in oxygen, I should say, and the changes in the export field, we also get a decrease in the N2O emissions in the beginning, and then towards the end of the simulation, we get an increase in the N2O emissions relative to pre-industrial. One can also compute from these sort of simulations how much this would affect the climate by using the classical feedback factor as used by physical climate scientists. For comparison, anthropogenic forcing by CO2 is about 2 watts per square meter, and here we talk about the forcing or a feedback of about a few milliwatts, 20 milliwatts per square meter in Kelvin, so the impact is rather small, but is, at least in the simulation, noticeable. So the conclusion here is we have a transient evolution of the meridional overturning circulation in the Atlantic, in the Pacific. We have an initial weakening followed by a more vigorous overturning under a warmer equilibrium, and the oxygen hazards, so low oxygen zones, expansion of low oxygen zones, are projected to aggravate over millennia, even after stabilization of radiative forcing and temperature. And meeting the Paris warming helps, of course, to limit this risk. This brings me then to the third example, and now I'm turning gear. I'm leaving the modern ocean and the future and go back to old times, basically to the last glacial maximum 20,000 years ago, and taking a look at how was the overturning circulation 20,000 years ago. Did it change over the glacial period? And this is fresh work done by Frederik Pöppelmeier, who joined our division and is working with our model. So the idea is we want to use a range of different water mass proxies, all introduced, thanks to Edouard again this morning, like delta Z13, like epsilon neodymium isotopes, protactinium thorium isotopes, or also radiocarbon, as they track water masses, water mass ages, and water mass distribution, and also overturning. And we have these tracers all implemented in the model, and so we can run the model with these tracers implemented, and we can do a perturbed parameter ensemble simulations. So that means that we force the model into different states, one where the overturning is weak and shallow, or where the overturning is very large and huge and reaches down to the bottom of the Atlantic, and so on. So Frederik in total produced 51 members for the last glacial maximum, and compared then the model outcome with the proxy data. He did also similar simulation for the glacial period, transient simulations, where he varied the salinity of the northern source, so in the North Atlantic, or of the southern source, so in the Weddell Sea, in this way by adding freshwater fluxes, but that could be, of course, another processes that happened in the real ocean back in time, but this was sort of the tuning knob to bring the Atlantic into different circulation states, which then can be compared with the data. So what you see here now is, again, a section from the surface to the deep ocean. The upper 1,000 meter still expanded for better visibility, and now it goes from the Pacific to the Southern Ocean to the Atlantic this time. And what you see here is delta Z13, this carbon isotope, stable carbon isotope ratio on a scale from minus 0.5 to 2 per mil, so from light to heavy ratios. And you can see the more positive values here in the surface ocean, also penetrating with the help of Atlantic meridional overturning into the Atlantic, and the very light concentrations here in the deep Pacific. And this is compared, the model results are sort of the background color and the contour lines, and this we can now compare with measurements, and the measurements are indicated here by these small circles. Each of the circles represents a measurement which has been taken at the same depth and latitude as the model is sampled either in the Atlantic or in the Pacific. And you can see the model is able to, or this particular realization is able to broadly represent the large-scale gradients that are depicted by the data. So you have also in the data, in these circles here, greenish color, and here light color. So the large-scale gradient is depicted. And this is for the LGM state, and one can also look at the anomalies, so the difference between the LGM and the pre-industrial. LGM means last glacial maximum, so 20,000 years ago when the expansion of terrestrial ice sheet was at its maximum. And when we look at these differences, you see here that the deep North Atlantic, the delta C13 has become more negative, even more negative, and the upper Atlantic has become more positive. And we focus on the Atlantic in this study. So this dipole pattern here indicates again a shallower Atlantic meridional overturning circulation at the LGM than at pre-industrial. And it seems that the model is able to pick up this signal. There are other tracers, as I mentioned. Luke Skinner will talk more about radiocarbon, so we may also compare the model results for the so-called benthic planktonic radiocarbon age. So that's basically nothing else than the difference in age between the surface ocean and the deep ocean as measured on foraminifera and other shells sampled in sediments. So basically, the water is young in the upper ocean and old in the deep Pacific. We have learned that by now, and the model sort of is able to pick up here observations. You say the observations sometimes also suggest quite large gradient in radiocarbon nearby water masses, which may be difficult to explain. So there are also caveats in the observations, as usual, when one is working with proxy data. We can then also look at the LGM minus pre-industrial difference, and then we see here again this dipole pattern, so larger ages in the deep ocean and younger ages in the upper ocean, so again indicative of a weakening of the Atlantic meridional overturning circulation at the LGM. So now this was a bit a hand-waving comparison. Frerk did a more sophisticated way, looking at the statistic. So basically calculate the mean absolute error taken as the difference between the model data and the proxy data. And he did this for these 51 members that we have in the model ensemble. And some of these members do a better job in representing the data than others. And you can see here this on a scale from 0 to 1. That's sort of the normalized mean absolute error for this data model difference. And on the y-axis, you see the depth of the Atlantic overturning circulation. Here turned northern source water, which seems maybe a bit more correct, but it's basically the same thing. So in the model, we also have a color tracer, which allows us to stay how deep this northern source water is actually penetrating the Atlantic. And at the equator, this seems for this tracer be at around 2.5 kilometers, whereas at pre-industrial, this depth is much deeper. It's about 3,600, 700 meters. So the conclusion just from this panel is that the depth of the northern source water, or of the AMOC, was about 900 meters shallower at LGM than at PI, as only a shallower AMOC is able to represent the observations for C13. And now you can guess what's coming next. we're looking now at other tracers. We're looking at the radiocarbon age, we're looking at epsilon neodymium, and we're looking at protactinium thorium isotopes. And basically, the 4 tracers give a consistent picture. You see here exactly the same panel. On the y-axis, this depth of the AMOC, and on the x-axis, this mean, normalized mean absolute error. And you see all the minima. The best model data agreement is found here in this area. So when the depth of this AMOC is shallower compared to pre-industrial. So basically, all tracers give a consistent result. We can do this exercise for this particular property, how deep the AMOC penetrates the ocean. We can also do it for another property, and that is the strength of the AMOC. So how fast is it overturning? And that's done in the next slide, or in the next 4 panels below. That's a bit more harder to constrain. As you can see, the signal is the results are a bit noisier, right? There's much more scatter in these points. But if you are somewhat generous, you see that all the tracers have the best results at somewhat weaker overturning. Here for C13, it would suggest C13 alone about 10 Sverdrup, whereas here radiocarbon age would suggest somewhere between 15 and 13 Sverdrups, epsilon neodymium somewhat lower, and protactinium thorium also somewhat higher. But overall, they all agree sort of that we need a less strong AMOC at the LGM to be consistent with this proxy information. And so the AMOC is reduced in the model from about 17 Sverdrups to somewhere around 12 Sverdrups, perhaps 14 Sverdrups, so some weakening. And as I mentioned, Frerk did this also for the deglacial period. I don't show the results here, but come just for the conclusion for the sake of time. So this multi-proxy analysis yields self-consistent results that the 4 different tracers agree with each other about the strength and the positioning of the Atlantic meridional overturning circulation. And the conclusion is the circulation was weaker, and it was also shallower at the LGM than at pre-industrial. And for those interested, the result for the Heinrich Stadio 1, so that is this cold period during 70.5 to 14.7 kilo years before present, and during the Younger Dryas, around 12,000 years before present, the AMOC was also reduced by about 50%, and similar during the Younger Dryas, but not a complete collapse. Do I still some time, Edouard? Yeah. So some thoughts on the role of circulation changes for the glacial CO2 increase. That's a long-standing problem. Basically, scientists are interested since the early 80s, when it was first measured on ice core that the CO2 concentration was low during the glacial period, to find out the mechanisms. And actually it goes back even further to the 19th centuries, when Arrhenius and Höckborn and others also thought that CO2 might have been lower during glacial time than during warm periods. And one question is, what are the drivers for this increase in atmospheric CO2 as reconstructed from ice core? Here are some results from the University of Bern that show here the evolution of CO2 over the past 25,000 years. So at the last glacial maximum, around 20,000 years ago, we have relatively stable concentrations, or I should say mixing ratio, otherwise Lilian will correct me, I recall that. It's always a mixing ratio in the atmosphere of about 190 ppm, then an increase by about 35 ppm, further increase is a slow side return, and then an increase to the early Holocene, that's the current warm period we are in, value of about 265 ppm. So during the glacial termination, during this phase, CO2 increased by about 75 or so ppm. And the multi-dollar question is, of course, what caused this increase and what role plays ocean circulation. And as the ocean is the largest, far the largest of the relatively rapidly exchanging carbon reservoir, land, atmosphere, ocean, and ocean sediments, people think that the ocean is really a key driver or regulator of these atmospheric CO2 variations, with perhaps contributions from the land, but the main thing comes from the ocean. Now, I'm looking again at data, and these are now data from a sediment core by Anderson and colleagues. Again, a time series from 25,000 years to today. And so here is this glacial termination during this period. And what do we see here? You see some wobbly curves. What do they tell us? We see here in red the delta C13 in surface water, or a proxy of it. And this delta C13 decreased here from the glacial period in the early part of the termination. And at the same time, as you can see by the blue curve, the flux of opal to the sediments in the Southern Ocean increased. So in the Southern Ocean, we see both an increase in the opal particle flux to the sediments and a decrease of delta C13 in the surface water. What does this tell us? If you have listened, then one plausible explanation of this is that this is indicative of an upwelling event, which brings nutrient, so silica, to produce the opal shells to the surface, and which brings delta C13 pore waters from the deep ocean to the surface. And so that's sort of the interpretation I put forward here as well. So we have sort of a ventilation event during this period, during this Heinrich Stadio 1, that we have an increase in ventilation, which leads to a drop in delta C13 and to a rise in opal sedimentation. And this is, of course, now representative of the Southern Ocean, not of the North Atlantic. And, well, we are in Europe, some maybe in east coast of North America. There's lots of ships and opportunity to investigate the North Atlantic, but we should never forget that the ocean actually is, the big thing is in the Southern Ocean and the Pacific, and the North Atlantic is a relatively small area. So for the global climate, we really have to think about the Pacific and the Southern Ocean. Now these are, okay, I continue here. So after this Heinrich Stadio 1, the opal flux remained high, C13 remained low, so the ventilation apparently remained high. Now we can say this is just one core from the Southern Ocean. There are about 2 other cores which show similar thing, but it's a local signal. Has it any global relevance? And for this, I turn back to the atmospheric record as recorded in Antarctic ice. And I look now at atmospheric delta C13, and you can see here again the same age scale from 25,000 to present. And you see here during this so-called Heinrich period, or mystery interval, as it's also called, there is a drop in atmospheric delta C13. And at the same time, there is a rise. And again, one can interpret this drop in delta C13 as increasing ventilation, which brings on the global scale delta C13 pore water to the surface, and at the same time carbon-rich water to the surface, which the hypothesis is then caused this initial rise in atmospheric CO2. Afterwards, delta C13 remained somewhat low for a few times, but then it started to rise. And for this rise, other processes needs to be invoked. My explanation would be that a large part of this increase is caused by warming, which reduces the air sea fractionation, so then you get about a 0.1 per mil change per degree of warming, and the surface water was warming by about 3 degrees Celsius, 4 degrees Celsius over the termination. And the other explanation is that the land carbon, especially in the early part of the Holocene, 10,000 years ago, when the climate warmed in the boreal zone, when the ice sheets of North America and Fennoscandinavia retracted, there was forests establishing and peatlands established, which took up a lot of carbon. So we can come back. So the indication is sort of we have a ventilation event in the early phase of the termination, but at least according to this proxy, not during the later part of the termination. We can then also compare the change here between CO2 and C13, and this gives a slope of about 120 ppm per mil. And now comes the model again into play. We can produce different ocean circulation states in the model and look how this affects CO2 and C13. And you see this here now on this axis, the radiocarbon age of the deep ocean below a depth of 2,000 meters, and this axis CO2 in some model units. And basically what you see is if the deep ocean gets better ventilated, so going from right to left, so from older ages to younger ages, then the CO2 is increasing. And we can do the same for delta C13, and you see exactly the opposite. When the ocean gets better ventilated, delta C13 is decreasing. So far, so good. What's the point now? We can now compare this CO2 to C13 slope. And in the ice core, we found about 120 ppm per mil, and the model suggests about minus 130 ppm per mil of this slope. So there's some agreement, and at least mechanistically, it seems that ventilation can explain this early CO2 rise of the deglacial period. So this brings me to the conclusion. This atmospheric delta C13 data, the data from the Southern Ocean on Opal and Southern Ocean surface water on delta C13 suggests an increase in upwelling during this Heinrich Stadio 1, 16,000 years ago, releasing CO2 to the atmosphere. We find similar slopes in the model than in the data, and the timing suggests then that this ventilation change is responsible for about 30 ppm of the deglacial CO2 increase. Then by interference, the rest must probably be other processes like coral reef growth, biological cycles, etc. So there's still a lot of opportunity. You may question these results. This is still a hypothesis. We still need to find ocean models and Earth system models that are able to simulate glacial, interglacial cycle self-consistently by representing all relevant processes, ice sheet growth, ocean overturning, atmospheric changes, marine ice, interaction with sediments. So there's a huge challenge for all of us still ahead. And with this, I am at the end. Thank you.